Alright, so let's just talk a bit about pressure here. I'm sure you've heard the word used a lot, but maybe you haven't seen the official definition, which is that pressure is force over area. So you've got some area and some force pushing straight in, and you can calculate the pressure like that. So really, if the force is pushing in diagonally, then you have to calculate what is the piece that's pushing straight in to the area, and that's the F that you use to calculate the pressure. I think you could put like a little symbol in the definition of pressure, that just symbol saying it's perpendicular to area or whatever makes sense. But I usually just remember, because of course the only thing that causes pressure is force that's pushing into the area. Alright, so pressure is force over area. That makes its units, well, you could say that it was a Newton per square meter, but we have a name for that, and it's a Pascal. So the unit for pressure is a Pascal, and the symbol is this capital P over here for pressure itself. Okay. So pressure is directly proportional to force, right? The more force you have, the more pressure you have, but it's inversely proportional to area. So the more area you have at a given force, the more area you have, the less pressure you'll have. So let's see if we can make a little sense of that. Well, pressure, when you get down to it, is the thing that hurts you, that'll like break your skin. So let's imagine that you have, your hand here. That's your hand, and somebody's going to step on it. Well, let's see. Let's say they weigh a certain amount. So we know that the force is going to be from gravity, right? The force of gravity is the force that's going to be causing this pressure. So they just weigh a certain amount. So let's say they're either going to stomp on you with like a regular shoe like that. Is this a shoe? I don't, sure. So some shoe like this, okay, ouch. Or they can step on you with like a stiletto heel, ouch, also. So I would prefer the boot from the heel. The heel would hurt more, right, in this, because of this pointy thing. So saying something is pointy, in other words, that is to say that it has a very small area, right? A very small area that's going to touch you, the surface area down there. And so the bigger the area, just looking up at the definition of pressure here, the bigger the area on the bottom, the smaller the pressure is going to be. Or in other words, the smaller the area, the bigger the pressure will be. Right, so a really small area, tip of a stiletto heel is going to really hurt when somebody of a given weight stands on you, as opposed to someone in a nice big shoe with a nice big surface area on the bottom of the shoe. That would hurt less to be stood on with. So that's just an intuitive way to sort of get a feel for pressure and what it is. Okay, so pressure isn't just about a person standing on you, or the single force pushing in, like in this picture kind of seems, but it can also be from, well, just air, which is simply because if there's enough air piled on top of you, that's going to cause some pressure, right? Or water. If you're deep underwater, there'll be a lot of pressure. But here on Earth, we know that the atmospheric pressure at sea level is about 1.01 times 10 to the 5th pascals. So there's that. Well, while we're on the topic, let's discuss Pascal's law,
which is something that can be used to show. I can spell.
Pascal's law, which essentially states if you have a small enclosed area of liquid, the pressure is going to be the same everywhere in that liquid. And Pascal's law could be something that can be used to show how like a lift or a hydraulic jack works. Okay, so let's imagine we have some simplified version of a hydraulic lift here. So it's just this bent tube, or is what I'm drawing anyways. and we've got like this plunger thing on this side, and another plunger thing on this side. And the big one is where you set what you want to lift, like I don't know, a car. Okay, there's my car. So the idea is, well, I can push down on this tiny one and lift up the car. Well, hopefully. So let's see, how could this possibly work? So in order to figure this one out, we make an assumption and we say that the pressure is the same everywhere in this water. That statement is basically Pascal's law. And that's a pretty good assumption. Unless the tube was really, really tall, then the pressure at the top might be less than the pressure at the bottom, but this thing is pretty flat. So we're going to say the pressure inside of it is the same everywhere. But we have also an area right here, right, a surface area of the liquid there, say A1, and a different surface area of the liquid here, A2, where these plungers hit. So I'm going to push down with this force F1, and I'm going to observe a different force pushing up here, F2. Okay, so let's see what we can do with this. Well, we said the pressure everywhere is the same, so I could say that the force over area, F1 over A1, is equal to that pressure, right? Because, you know, that's the definition. But also the pressure is the same on this side, so F2 over A2 is also equal to that pressure. So ignore the pressure, and say I solve for F2, multiply over A2, and I get that F2 is equal to F1 over A1 from that side, times, I'm multiplying over A2. And I'm going to go ahead and just, using fraction rules, write the A1 right there instead, because then it shows how it's like a piece of F2 is a fraction of F1. Depending on it. So if I said that A1 is smaller than A2, or that's what I've drawn, so A2 over A1 will give me a number bigger than 1, right, because A2 is bigger than A1, so I've got an improper fraction here, or a number greater than 1. And so I'm actually saying that F2 is a larger force than F1 in this case. And so yeah, you push down with a little force that your arms are capable of here, and if this thing is built right, you'll get a force capable of lifting a car out the other side. Which sounds, it sounds kind of crazy and impossible, like it might violate some kind of law, and it doesn't. It turns out with a further analysis of this problem, we find that, you know, say you push down an entire foot. Oh, I'd said a foot. How about a meter? That's more physicsy. Say you push down an entire meter over here. Well, your car will probably only raise like a centimeter. So that's why, and they're built a little bit differently. But a hand, like a shop jack, a hand jack that you might actually own, has this pump thing on it, and you have to go back and forth, 1, 2, 1, 2, 1, 2. And so what you're doing is you're doing this a bunch of times, basically. You're moving your arm for like total of many meters just to move your car up like half a meter so you can crawl under it, right? But it's all just because of Pascal's law.